Hello, everybody. Welcome to my talk. My name's Neil Hickey from ARM. I'd like, in my talk titled Orc Class for Dragons, to present how we make use of LLVM currently for GPU in our GPU compilation flow. And the main focus of this talk is to open up a dialogue with LLVM experts of how we can improve things, maybe make some modifications to the IR itself to better support GPU compilation. So I'll briefly describe the execution model used on GPUs, and some of the different languages which are used by people to develop for GPUs, both from compute and graphics side. I'll present a brief introduction to Vulkan, some of the semantics within Vulkan and how we currently map this to LLVM IR, and hopefully discuss how we can ideally improve things. And also present some of the other tools that are out there for GPU execution, different frameworks, and how they use LLVM as well. So I don't intend really to be presenting solutions in this talk. I really would prefer to open up the dialogue to everybody and see how we can improve how we use LLVM. So I'll start with a brief introduction of the execution model for GPUs and how it differs from a CPU. So in a typical CPU application, you might have multiple different instruction streams which map to different threads on the CPU, and these are totally independent. There are some synchronization opportunities between them, so you can obviously set semaphores and waits between different threads to synchronize, but they essentially happen independently. And this is a little bit different than how things work on a GPU. So GPUs typically, in order to get some of the performance that they promise, have multiple threads which all execute in lockstep and execute the same set of instructions and the same instruction stream, but it operates on different data. So within a single GPU, you may still have different instruction streams happening, but each instruction stream maps to multiple threads and multiple processing elements that happen and process in lockstep. So some of the different languages that we have for GPUs, OpenCL, mainly focusing on compute. Obviously, we also have CUDA and SQL. I think Michael presented yesterday about the different compute languages. On the graphics side, traditionally we had GLSL, which was desktop, ESSL, which is more for embedded and mobile. And nowadays, obviously, we have Vulkan, and Vulkan has a unified language for targeting both mobile and desktop. So taking a brief look at OpenCL, it's a typical naive implementation of a matrix multiply. So we have multiple loops iterating through the result matrix, walking over the two input matrices, row and column, and computing a final result. So this is how it might be implemented on a CPU. In OpenCL, it looks a little bit differently. So the two levels of the loop nest that I presented earlier are actually represented by the execution on the GPU itself. So each thread that executes on a single processing element within the GPU is doing the inner loop. And then there's a matrix of threads which are all executing in lockstep. So each thread is responsible for computing a single result value from the matrix. And you can see here that the way that each thread finds out which result value and which input values it needs to operate on is it queries its own invocation ID. So we have both an X and Y coordinate. You can also have a Z coordinate, so you can do three-dimensional dispatches. But this is showing the X and Y for the result matrix, which it queries from the runtime and calculates the final result. So typical graphics applications make use of very similar concepts. So graphics is obviously a domain-specific language to do graphics. So it uses them in different ways, but it's largely the same concept. There are multiple threads happening simultaneously, doing different things. So here I'm just displaying the graphics pipeline. So the blue boxes are things which are programmable. So you have vertex, tessellation, geometry, and fragment processing. I'll not really touch on tessellation and geometry. It's not really that relevant, and both of those stages are kind of optional within the graphics pipeline. The main two are vertex and fragment. So a vertex shader will take each vertex of your geometry mesh perform different calculations on it, output the vertex for going into the rasterization stage, and the fragment processor is responsible for taking each pixel in the final image and applying any transformations and calculations to produce the final color. So all of these programmable stages, similar to OpenCL or similar to a single kernel invocation in the OpenCL world, and they map to a single thread group on the GPU. So multiple threads are executed together in lockstep, and you can similarly do some data sharing between the different threads which are executing, but largely they are operating on separate pieces of data. So the Vulkan shading language, which is Chronos standard, it has lots of similar concepts to OpenCL. It strongly correlates to the GPU execution model that I presented earlier, and is targeting massively parallel GPU devices. So it has similar concepts, as I mentioned, so it has vectors and matrices of primitive types, but it also has more complicated types, such as images and samplers. And these are used to provide texturing onto the fragments. It can also communicate amongst its neighboring threads that are executing using subgroup operations to calculate derivatives. And one of the main things that I guess it introduces, which is different than CPU, is the concept of different storage classes. So I'll shortly, briefly explain what those are within Vulkan and the different memory models, memory addresses that we have. But obviously within LLVM, we make use of address spaces to represent them, which has a number of problems for us, which I will describe briefly. So taking an example of a simple Vulkan GLSL application. So this is a simple vertex shader. It takes a single input position and simply writes out to the output position the value that we received from the runtime. In this as well, we specify the location of the input attribute position. So the runtime will have set up a data structure of attribute values for passing into the vertex. So this is representing which location within the input buffer from the runtime do I actually want to execute? Do I actually want to map to my position variable? So how we currently represent that in LLVM is by using different address spaces. So here 5 and 6 are used to represent the in and out address spaces for the vertex shader. The location has also been captured in a piece of metadata, because this is needed in order to produce the final shader binary. So we make use of metadata to capture the location information currently. Any optimizations that want to operate on this sort of have to recreate the semantics information from reading and parsing the metadata, and obviously need to understand what address space 5 and address space 6 actually match to and what they represent. So this does cause some issues and can limit the ability of using some of the standard LLVM optimizations, because the LLVM optimizations themselves, they don't understand what address space 5 and address space 6 mean. They don't understand those semantics and typically have to act very conservatively in the face of them. So we can't perform some optimizations we might want to without writing, bespoke specific optimizations ourselves. So Vulkan introduces lots of different address spaces which need to be handled. As described, we have in and out, but we also have different representations of constant values. So push constants and uniforms. These are constant from the point of view of a single invocation. The value will not change, but they're set by the runtime after compile time. So they're not compile time constants, but they're set by the runtime. But we know that they'll be constant throughout the entire execution of that particular shader. And one of the issues we have here, as I mentioned, so LLVM natively doesn't understand these address spaces or how to handle them. And lots of the optimizations we might want to run, therefore, can't operate at this level. And all of these memory regions and storage classes have unique semantics. And as mentioned, we have to write specific optimizations which can understand them. Additionally, the problem is that there are multiple tools which make use of LLVM to target different graphics applications, and they all map address spaces slightly differently. So some of the tools that I wish to describe today, so one is the SPIR-V to LLVM translator, which we're working on as part of Kronos. There's also DXIL, which is a Microsoft fork of Clang and LLVM, and is primarily used to target HLSL. And then there's also NVIDIA's NVVM, which is used as part of CUDA. And they all have a slightly different mapping from these higher level concepts to the specific address spaces that are used. So the generic concept within OpenCL allows you to have pointers to different memory regions, but you wouldn't necessarily want to have a single function or multiple functions to target each different address space. So OpenCL has a concept of generic pointers. So the actual address space the pointer points to is not specified, but you cast between generic pointers and the specific address space pointers. So this is quite important because obviously it has an impact on how you perform optimizations. Unfortunately, all the tools that I've mentioned, they all have a slightly different way of mapping this to the given address spaces within LLVM. And similarly, some of the other high-level concepts, such as private memory, also map to slightly different address spaces in the different tools. So this means that for each of these individual tool offerings, they have to write their own optimizations to represent the semantics of these features. And I feel this is some way that maybe we could extend LLVM to capture some of the semantics of these address spaces in LLVM itself, rather than just making use of address spaces. Of course, the problems here would be actually which set of address spaces or storage classes would we want to capture. Probably capturing all of them in LLVM itself would be a little bit too much. And for lots of the phases, the optimizations that we have, it's not really that crucial, the exact semantics of a particular address space. But some, such as global and uniform and constant, as expressed here, it would be valuable to have those concrete representations in LLVM so that we could perform optimizations and make sure that all the existing LLVM optimizations work correctly in the face of these address spaces. So one of the other concepts within Vulkan which are difficult to represent correctly, accurately in LLVM without using metadata, you can specify the structure of, so the offset of structures and the layout of structures explicitly in Vulkan. You also have different padding rules used by the different structs within your shader. And it's difficult to represent that directly in LLVM because obviously LLVM has a single view of structures and everything's very flat and there are no holes. Whereas in Vulkan, you can actually specify a struct and specify the offset of each individual variable, and they can even be out of order. So the application, how it's ordered in the application, you can specify the offsets explicitly and it can actually be essentially reordered. So representing that in LLVM is quite challenging. We have to represent that largely by making use of metadata currently. And again, then the optimizations have to recreate that data as the transformation passes are running in order to rebuild the semantic information of how the structure is structured. So as mentioned, you can specify different memory layouts for the structs. Most of these are not used anymore in Vulkan, the top two, but we still have the bottom two. All they really represent is slightly different way of laying out and padding the variables within your struct. But obviously within LLVM, we only have a single data layout sequence, so it's difficult to express this different features within LLVM itself. So what we currently do is we make use of metadata, as I mentioned. So here we're just attaching the metadata to the declaration of the variable. And then anything which wants to process this has to deserialize essentially the metadata again and understand the semantics. This could be an area as well where we could extend LLVM to allow these types of layout and offset specifications in the structure itself, such that we didn't have to make use of metadata in this way. I'm not going into much detail on this now, but each of these variables within the struct as well, if it was an input or an output block, they can have an explicit offset, as I mentioned earlier. So currently within LLVM, we have to pad everything. So if you had, for instance, if the top one had an offset of 10, you'd have to pad it with 10 bytes of data prior to the start of ARP variable, which is inefficient both from having to express all that extra data within the LLVM module itself, but also when coming back from LLVM into something such as SPIR-V, we want to recreate that original structure layout. So we lose a lot of the information going through the LLVM. Okay, so this is another example of specifying input variables. You can specify a given location. You can also specify a component. So in the top expression, this would actually be two variables, both in location 0 and location 1, but only the first component within that location. Again, this is another case where we have to use metadata to express this concept within LLVM. So we're looking for ideas of how we can more accurately represent this. The main one really for us, though, as I mentioned, is representing the address spaces correctly. This has big issues for optimizations. They have to be very conservative currently. So an example of a special optimization which has been implemented here is the infer address space from NVIDIA. So for the generic address space, they had to work out by pausing the code exactly which address space was the original one handled. And this introduces extra runtime in the optimizations, but also means that lots of the other optimizations have to make sure that runs first in order to remove the generic address space. Okay, great. Thank you very much.
Are there any questions to Neil? Yeah.
Hey, thanks for the talk. So other than alias analysis, which is very conservative about address spaces, in that it doesn't use it at all, do you have any other examples where core LLVM transformations don't work because of the presence of an address space?
So I think some of inst combine can't make some transformations in the case of different address spaces. So it has to be quite conservative. There are quite a few other optimizations which will essentially say if an address space is applied to this pointer, because I can't reason about those semantics, it has to stop in that case and just kind of drops out. So if LLVM had these concepts as part of the IR itself, then obviously we could implement optimizations in a more generic way which could handle how this works.
Other questions? Yeah.
Hey, I didn't quite get why. So in case of the structure padding, why can't you just use like an artificial structure within a structure to pad the data, and why do you need to introduce metadata to tell how the structure is laid out? It seems that it would be simpler and you wouldn't need to write your custom optimizations to handle metadata.
Yeah, so one of the things that maybe I didn't talk about is the SPIR-V to LLVM translator is sort of bidirectional, so it wants to both go to LLVM as well as coming back out again to SPIR-V. So it's important to maintain the semantic information such that we can regenerate the original SPIR-V afterwards, which is one of the main reasons why we make use of metadata in that way, in that particular case. There may be some optimizations you could do if you didn't have to pad things, so you could pack things more efficiently, make use of more sort of vectored loads for some of the data. If you know that actually the stuff in between is essentially not there, you could introduce optimizations that way.
We have time for more questions.
So in case of the address space conflict, how do you handle the address space in different module?
Sorry, can you repeat?
I mean, if you have an address space conflict in different module, How do we handle it?
Address space conflict, I'm not sure.
Yeah, it could be in one module that, I mean, if you inline, then you have a conflict. It might happen, right?
So I'm not sure.
I mean, if you have some parameter passing,
Sure.
then in one case it's generic, and the other case could be global, if possible.
Oh, okay. So I mean, prior to calling
Yeah.
the function, you do an address space cast between
Yes.
the specific to the generic one. Obviously, there are optimizations or checks within LVM itself, which make sure that you can't just use one pointer with a particular address space in a different situation, because it would be invalid. Therefore, you'd get a parser error. But so it's, in the specific case of generic, it has a given meaning, so you can pass in global or other address spaces, and it works fine. But ordinarily, that wouldn't happen. You'd get an error saying that the address spaces don't match.
We have time for one more question. No question? Okay, let's thank our speaker.